field. Okay, let me do again. So if you have stress X at point I, right? So this is equal, so we know that's under tensile mz over izz multiplied by y2. And you realize that stress X at point J is also equal to mz over izz multiplied by y2. So when this is the case, you realize that stress X at point I is equal to stress X at point J, right? So the same apply for loading condition number 2, right? So for loading condition number 2, as you can see, alpha and beta will have the same stress state. I and J will have the same stress state. So symmetrical bending is based on the stress state rather than geometry of the structure or symmetrical loading of the structure. Okay, so as long as these conditions are met, okay, it's not asymmetrical loading, period. Okay, so a lot of times it seems to be obvious. Why is that? Because when we look at when the term symmetrical and unsymmetrical, our mind automatically comes into the mindset of what? Geometry. Yes or no? Right? It's not. Okay. It is a what? Stress state. So in solid mechanics, okay. So in the field of solid mechanics, which what you're learning now, symmetrical and unsymmetrical condition is a stress field condition, not a geometry condition. Okay, I repeat again, it is a stress field condition. Right. So now I'm just showing you what do we mean by symmetrical. So the next one I'm going to show you is what do I mean, or what do we mean by unsymmetrical. Okay, what do we mean by unsymmetrical? So in unsymmetrical, we still focus on centric bending. Okay, with you. So now I'm going to do, I'm going to sketch a 3D structure. Okay, so this structure over here, we have a beam. Right. And then this is supported by, this is our structure. Right. And this is built in. And this is built in into a wall. And then we have I'm going to draw our axis. So this direction over here, okay, so this is our x, And then like before, this is our Y. And then one more. That is our Z. Okay. So this is our X, our Y, our Z. Okay. And then we have an applied moment. And the applied moment is such that I'm going to find. So this is the applied moment, M. Okay. And the applied moment, I wonder how can I draw this? The applied moment, if this work, maybe it will not work. Okay, it will not work. Let me, yeah, it does not. So the applied moment, okay, the applied moment only have two vectors. Okay, so the applied moment, let me write this down. The applied moment, M, okay, the applied moment, M, is acting, okay, acting on the YZ plane only. Okay, so YZ plane is this plane over here. Okay, so this is our YZ plane. So this moment over here, this applied moment M has two components only. Okay, so the two components are, we have MZ and we have MY. Right? We have MZ and MY, and we have a theta theta about the about the x-axis. So theta is measured about the x-axis. Okay. So now we know from here, we know that my is equal to m sine theta x. And we are also aware that we have mz is equal to m cos theta measured in the x direction. Okay. Now, so from here, we are going to use right-hand rule. And by using right-hand rule, right, we know we can sketch the moment vector. Okay. So the moment vector for my using right-hand rule, this is my, right? And mx doing mz using right-hand rule is in this direction. Okay. So once you got that moment vector, you know what is positive and what is what negative. Okay. So from here, I'm going to label 4 points. So this is my alpha. Oh, okay. I'll not. Yeah. I'll not label there because it's not necessary. So I'm going to label over here. This is my point alpha, point beta. This is my point I. And if I were to sketch the hidden detail, okay, if I were to sketch over here, this is our J. Okay, that's our J. So now we're going to view this, okay, in 2D now. Okay, so now, most of the time when we apply right hand rule, we can get a bit confusing regarding the moment. So I'm gonna help you remember. Okay. So remember I told you guys, right? So if or this is in fact this is the first time you are seeing it, not I have to. So if this is our moment based on right hand rule, right? Based on right hand, this is the moment vector. So this is compression, right? This is tensor. Okay. So now if the moment is applied in a different direction, let me tell what different direction. Now if the moment is going downwards, okay, so I'm going to like rotate, flip vertical, right? Now compression is on the right hand side, tension is on the left hand side. Okay, or let me, so if now your moment is coming down this way, right? So by using right hand rule, right? How you grab, so the moment vector, oh no, it's not, sorry. So by when you grab, it will come this way. I do apologize. In fact, I don't think I should mirror this. Okay, I'll tell you what. You should rotate. Okay, so I do apologize. It's not a flip. So if I paste, right, and then if I now rotate, it doesn't allow me to rotate. Rotate right and rotate right again. Now you see it. Okay, it's not flip. Okay, it's different. So now when the moment is coming down, how your finger close, now the left hand side is compression. And then what if it's horizontal? Okay, what if now it is horizontal? So I will. So when you're sitting for a test, you're not sure, you just draw one direction and rotate your paper. Okay, and rotate your paper. So now if the moment is going towards the right, okay, we are okay. So now the top is tension, the bottom is compression. And then if the moment is going towards the left, hey, no, left. Okay, now it changes. Okay, so it's like rotating your paper. So now, if you were to look at Y now, right, which correspond to this, right? And then if you look at Z now, right, if you look at Z now, Z correspond to this. Yes or no? Right? So now you can more or less recognize what is positive or what is compression and what is tensor. This is by visualizing using moment vector. If not, you have to remember where the center of curvature is, and then you have to remember whether is it Y positive, Y negative. It gets too confusing. Okay, so use this. It's so much easier. I've done a lot of calculation based on this. It's so easy to do. Okay, right. So now we are going to look at the stress state at point alpha, beta, I, and J. Okay. So I'm going to now draw out. So now we are going to have a different view. We are going to view in a 2D world now. Okay, we are going to go into a 2D world. But before we go to a 2D world, we take a 5 minutes break. We come back, we look into a 2D view.